So, ladies and gentlemen, esteemed colleagues, fellow innovators in the world of finance, welcome to this session. My name is Dragan Korik. I'm a senior go-to-market specialist from AWS focusing on databases. I'm based out of Stockholm, Sweden, and it's with a great pleasure I stand with you today. Over the past decade, we have seen huge transformation in the financial landscape. FSI segment has not just grown, it has exploded. The underpinning technology which has been supporting the growth is among us, and we can see the growth. What we have seen as well is the millennium shift, the generational shift from millennials to Gen Z, digital natives. They are the primary users of the financial services. They value speed, confidence or capabilities, but they also expect digital channels. They don't just expect them, they count on them. But perhaps one of the most exciting transformations was the rise of the real-time credit assessments, something we have gathered today to discuss. The lending has been part of the financial services for such a long time. However, the technology rise supported by Gen AI, supported by machine learning, artificial intelligence, is going to revolutionize this segment. Imagine loan applications being processed not within the weeks, not within the day, but seconds, minutes. Today we will focus on a story from Klarna, which is going to showcase the benefits being achieved with this technology, starting from operational efficiency, cost reductions, risk mitigations, etc. Trust me, it will be worthwhile staying with us, worthwhile your time, and also the story which is going to be presented. So, ladies and gentlemen, please join me welcoming Mr. Tony Lee from Klarna.
Thank you, Dragan, for the introduction. Can you hear me all right? Thumbs up? Yeah, perfect. All right, happy to be here and happy to see so many faces excited about data processing. So today I'm gonna share with you how you can minimize risk on your data processing systems, how you can make your data processing systems more cost efficient and scalable, how you can reduce the differences between your real-time and batch processing layers, and how you can enable fast feature engineering iterations on top of your processed data. So I'm going to share a story of a journey we made at Klarna to address exactly these 4 points to improve one of our data processing systems. My name is Tony. I work as a senior engineer and competence lead at Klarna, based in Stockholm, Sweden. I've been at Klarna and in the data processing space for 4 years now, and currently I'm the technical lead for the team responsible for creating customer features for credit underwriting. So today I'm going to share some insights and learnings from the project we have driven in our team to improve the data processing for creating customer features for credit underwriting. And the ideas and solutions that I'm going to share today are not perfect for every scenario, but it's something that we have found works well in our problem space and our application. And I hope that you can take some inspiration and ideas from the presentation today and hopefully apply that to your own systems. So I'm going to start off with talking about credit underwriting and more specifically about customer features and customer data points for credit underwriting. And then I'm going to dive into the history and context about our setup and our system, everyone's favorite subject. But this is more to kind of highlight and showcase the pain points we had before and the issues we had and what the problems we're trying to solve. And then lastly, I'm gonna go into the system architecture of the current solution, and more specifically looking at system diagrams and some concrete examples to showcase how our updating of our intermediate state and our data model looks like, how our feature calculation works in real time on request, and also how our offline processing setup looks like. But first of all, you might be wondering, what is Klarna? Can I see a show of hands of how many people has heard of Klarna before? Yeah, cool. And how many has used Klarna before out of you? Perfect. So this next section is for everyone else that didn't raise their hands here. So Klarna is a fintech company from Sweden, and we provide payment solutions and products that enhance the customer experience or customer shopping experience. So our goal is to give more control and flexibility into the hands of the consumers. You might know Klarna as a buy now, pay later company, but we offer so much more in the e-commerce and shopping space. And some examples of that is the Klarna app, Klarna card, the cashback program, and much more. So we are a global company that reaches 87 million active consumers, working with over 600,000 retail partners across 27 different markets. And each year we transact around $100 billion in volume, and we not only have a strong presence online, but also offline in physical stores. Klarna has Klarna has a diverse network of merchants across different categories. So not only retail and fashion, but also everyday subscriptions, travel, electronics, and much more. And here are some examples of the global brands you might know of that provide Klarna as a solution. We at Klarna have a very diverse customer base across genders, educational levels, income levels, and living areas. And we have very responsible payers. Around 99% of our consumer balances are paid. And also something to consider is that we generally have a lower outstanding credit amount on the average consumer. So at Klarna we have an average of $160 per consumer, and that you can compare with around $6,500 for an average credit card user. So that's 60 times lower risk that the consumer is carrying. And although we offer buy now, pay later solutions and payment options, actually 29% of our customers choose to pay the full amount upfront as well. So now that you know a little bit more about Klarna and the scale we operate at, let's dive into the problem space of credit underwriting. And more specifically about customer features and customer data points used for credit underwriting. So for Klarna as a payment service provider, it is very important for us that we can correctly and accurately assess the risk of purchases, right? And this we do with a high frequency on every single purchase. We make a risk assessment. That is because we want the most up-to-date view of the customer profile at the time of purchase, whenever we accept or reject the purchase. And one key aspect of making these risk assessments is the data feeding it, and the customer data points and customer features that are feeding the credit underwriting process. So credit underwriting is boiled down to the very core, is basically about accepting or rejecting a purchase on a customer. So making those decisions are underwriting policies and credit models. And those both are fed by data and powered by data, and that in Klarna consists of our internal Klarna data, the external data from credit bureaus, and also some information on the transaction itself. So the data itself feeds into our policies and credit models, which in the end makes a decision to accept or reject a purchase. Underwriting policies is basically a set of rules with some thresholds that in the end decides if you accept or reject or not. So you can think of it as a kind of flow chart with accept or reject as the end state of it. And these policies often have rules that are related to what we call hard rejects. So they can be, for example, related to compliance or regulatory reasons. The policies are manually defined, and they can also, the thresholds in the policies can also be tuned and adjusted to kind of meet your business goals. Credit models are machine learning models that are used to predict the probability of a purchase defaulting. And these machine learning models are trained on historical data. And since they are machine learning models, they also require quite a large amount of data to have the ability to generalize well on new customers and new cases, right? So, and it also helps if we have refined data points that feeds into the models and reduce the noise we have in the input data itself. In the end, the model outputs a model score that corresponds to the probability of the customer defaulting. And this is then used in the credit policy to make the decisions. So both the policy and the model itself are powered by data, right? But today we're going to focus on our internal data from Klarna, and more specifically about internal customer features. So one of my team members made this definitions that I like, which is descriptive and accurate, and that is an internal customer feature is a reduction of aggregated internal data to digestible pieces of information. So basically, it's useful and predictive data points on the customer that basically says if the customer are able to pay in the end or not. So some very simple examples of what these could look like is how much debt does the customer currently owe to Klarna? How much has the customer paid to Klarna? When was the first time the customer ordered with Klarna? And has the customer ever been late on a payment to Klarna? And why are these internal features so important? So we do get data from our external bureaus, right, or for our credit bureaus, and they are very important to make accurate and predictive, accurate risk assessments in our policy and our models. But these data points are not updated on a very frequent basis. So this becomes very important for our returning and loyal customers because our internal data can be updated in real time, and we can consider customer actions immediately when they are made. So for example, if a customer places an order, we want the subsequent purchase to kind of consider that new order and be less strict about, or be a bit more strict about the next purchase, right? And the same the other way around, if the customer pays off an existing debt, we want to kind of allow a bit more on the next purchase, so on. So to summarize this, we basically have our external credit bureau data, and on top of that, we add our internal real-time data to get a more complete picture of the customer profile at the time of purchase. So with that, you know a bit more about the problem space itself and credit underwriting. We can move on to the history and technical context of our system. So now we're gonna show the previous setup of how our system looked like, and this is basically to showcase our pain points that we have and the issues we had before, and what we're trying to solve with the new architecture. So here's an overview of our previous setup, and it starts from the source systems on the left side here, with some internal databases, and then ends on the right side here with the underwriting policy itself. So if we start from the source systems, in this example we have system ABC. They have their internal databases, and that is exported on a scheduled basis to S3. So they basically export a snapshot and a dump of their internal database to S3. Then we had a batch feature system that was running on Amazon EMR that would process this snapshots of databases and then create features and then output that to a feature dataset on S3. And then this dataset is uploaded to a DynamoDB table, which is then accessed by our feature service that serves the actual values to the underwriting policy to the right here. And for a subset of features that we have that are very important and time sensitive, we have a real-time requirement. So that's why we have the system on the top here, which is the real-time feature system. That is using the output of the batch feature system, the latest feature values there that's calculated, and then on top of that adds a real-time contribution or a real-time delta on top of it to kind of get the most recent view of the feature values. And this is read from a message queue. In Klarna, this was Kafka. And then to note here, this message queue only exists for a subset of systems. So in this case, only system C is producing the real-time events here. So then the underwriting policy calls the real-time feature system or the batch feature system for the feature it needs for the policy and decision. And then it basically logs all the decisions with its corresponding feature values to a log in S3. And then analysts and data scientists go to this log to extract the feature values so they can create their training data sets and their analysis data sets that they then can train models on in SageMaker or do further analysis in Redshift. So there are some issues with this setup. I will name 4 of them, or the 4 biggest one today, and basically we're gonna later on kind of show how we solve them with a new solution. So first of all, we're relying on the internal database dumps as source for our batch features. And what this means is that we don't have any contract between our system A producing the data itself and our batch feature system. So what used to happen, or what has happened before at Klarna, was that we had some incident or bugs caused by system A wanting to do an internal change to our internal database, but then not knowing that the batch feature system is actually relying on that internal field or whatever in the database. And that basically caused the feature distribution to shift a lot, which then influences the underwriting policy, right? So that's bad. So the other issue, the second one, is that our batch feature system is processing snapshots of the internal database dumps, right? So it basically needs to reprocess all history of data every single time it runs. And this was usually on a daily basis or every other day. And with Klarna's growth, this quickly became very costly and not very scalable, right? The third issue with this setup is that we have a big difference between our real-time layer and our batch processing system. So first of all, they were implemented in different languages, using different frameworks, and being run on different infrastructure. And also on top of that, it was also managed by different teams. So this means that if you wanted to change a feature or add a new feature, you kind of need to know about both systems, and you need to make sure that your behavior is like propagated in the same way through the real-time and the batch layer. And this added so much friction that basically it's halted feature engineering innovation. So we basically started off with a set of feature, and then it was so much friction that no one kind of changed that or added anything new to that. So we were kind of stuck with the same features for a long time. The last issue that we have is considering the part on the right here. And that is that we need to wait for data to mature. And what that means is that the policy is extracting the feature values from real decisions in production, right? And then the model training and the analysis is done on actual production calls from the policy. More specifically, it will basically mean that if you want to experiment with a new feature and you want to assess the usefulness of it, you would first of all implement your new feature in both your real-time and batch system. You need to bring it live, and then you need to make sure that the underwriting policy is requesting that feature and logging it to S3. And then you need to wait for X amount of time, depending on your use case, because you want to gather a significant amount of data, and sometimes you want to know the end of the life cycle of the purchases, right? So this usually could mean months or weeks before you could really assess the impact or assess the usefulness of your feature. And if you were unlucky and it didn't meet your kind of expectations and was not useful in the end, you need to like reiterate this whole process, right? So very long iteration here. So if we list all of these four issues, we can also list the corresponding ideal scenario that we would want instead. So instead of relying on internal system database dumps as the data source, we would want a solution that have a strict contract between the producers and consumers. Instead of relying on daily transformations on all history, we would want something that's more cost efficient and more scalable for Klarna's growth. Instead of having a split real-time and batch implementation, we would ideally want to have minimal differences between our batch and real-time processing layers. And then instead of needing to wait for data to mature, we'd want a tool that allows us to experiment with new features on existing and historical data. So now we can dive into the current solution and the system architecture of the current solution. And this new solution is trying to assess exactly these 4 points that we listed here before. So let's start off with an overview of the new solution itself. And one thing you might notice, or one thing we can start off with, is up in the top left corner here, we have our data sources, but now there are event streams or message queues instead of the internal database dumps. And here we have clearly defined schemas with clearly defined events defined by the producer itself, and then which means that we have a strict contract between our producer and consumer. In Klarna, these data sources or message queues are Kafka topics. What this means is that the consumer can make the right interpretation of data, right assumptions of data, and the producers, they know which systems are depending on the data and can make announcement on changes and knows how changes in the data itself will impact the downstream systems. And this, of course, is not just a single change or an easy change by a single team at Klarna. So this was more of an organizational effort to move to this way of communicating data between teams instead of relying on internal database exports. If we go back to the diagram again, we essentially have two parts. So on the top here, we have the real-time processing part, and on the bottom, we have the offline processing part. And these two are kind of glued together with something we call the business logic library in the middle here. So the business logic libraries are basically the business logic implementations extracted out of the applications themselves. So they are agnostic to the runtime, they're agnostic to the infrastructure it's running on. What that means is that we can use the same feature definitions and the same business logic implementations across both the real-time layer and the batch layer without caring where it's being run, right? So if we focus a bit more on the real-time processing layer to start with, it basically consists of two sides. So the first one being the update state side, which writes data to DynamoDB. And then we have a read part, which does the feature calculation that basically reads data from DynamoDB. So on a high level, the events come from the data sources. We process that data in our update state application running on ECS. It uses the business logic library to update the state, write it to DynamoDB. And then on the right side here, we have the underwriting policy that makes a call to our feature calculation service that then fetches the states from DynamoDB and applies the feature calculation defined in the business logic library and returns it to the policy. And here in the middle, in the DynamoDB, we're basically storing intermediate states with a specific domain-specific data model. In Klarna, this is on an order level, so we have one order per DynamoDB item, right? Yeah, we'll see some examples of that. But here we have basically a choice to make as the developer and designer of the system. So one thing you can consider is how much you put on the write side and how much you put on the read side. So if you put more transformations and more calculations on the right side here, and pre-aggregate a lot of data on your update state logic, you will need to do less on your read side, right? So you gain more read performance. While vice versa, if you do more on the read side and keep a more generalized data model, you gain a lot of flexibility when you're reading the data itself, but at the cost of performance, right? So basically a trade-off that you can do. Looking at an example of how the table definition of our state table can look like. This is something applied to our problem space, but as the partition key, we have the order ID here, so we have one DynamoDB item per order, and then we have a bunch of other attributes, important one being customer ID, which we use as the global secondary index, so we can query the order states based on the customer ID itself, and then the actual state itself, right? So the state of the order encoded. And here is an example with some mock data in it. So on the left side here, we have a bunch of UUIDs in the ID fields, and then we have the state attribute with the actual state of the order encoded. So if we talk a little bit more about how we update the intermediate state and the data model itself, we can focus in on the left side of the previous diagram, right? So basically what happens is we get an event from the data source that is consumed by our update state application. That application then goes to our DynamoDB, fetches the current state of the order, and then applies the event on the current state based on our business logic library. And then you get an updated state, and then you write it back. So looking at the more concrete example to kind of showcase exactly how this looks like, let's say we have an event that's telling us customer 1 paid on order 1 with the amount 123. Then our application would go to our DynamoDB state table and say, give me the current state of order 1. So let's say we have a current state that looks like this. That's basically we have order 1 on customer 1 with an outstanding 123, but no paid amount because the customer hasn't paid yet. Then in the business logic definition, we have defined how we process these events. And this one is very simple. We say, okay, the status is paid, so we set the paid amount on the states to the amount we get from the event itself. So if you combine all of these three, so applying the event on top of the current state, using the business logic that we have defined for that event, we can get a updated state that has the paid amount to 123, right? And then we basically write this back to the state table. And this is how we update the states. So now we can look at the other side of the DynamoDB state table, and that's the feature calculation we do on request. So the policy, underwriting policy makes a request to our feature calculation service, and it asks for a set of features on a specific customer. And then on our feature calculation application, we'll then query the DynamoDB on the global secondary index on that specific customer to get all the states we have. And given that set of states, we can then apply our feature definition to get a feature value, and then we return it back to the policy itself. And also here, looking at a concrete example, let's say we have a super simple feature that's called paid amount. So we have defined it in this way. It takes a list of states and then sums up the paid amount on each state, right? Then if we have an example request on the left side here from the policy itself, that's requesting a set of features on customer 1. So in this case, we have paid amount and something else we don't care about right now. Then our feature calculation service goes to the DynamoDB table, fetches the current state that we have on that customer. In this case, we only have one order, but you can have multiple orders here then. And then we have our example from before. You have order 1 on customer 1 with paid amount 123. So then if you take the return states and then feed it through your feature definition, you basically get paid amount equals to 123. Easy, right? So that basically sums it up for the real-time processing part. So now we can dive into the offline processing part, which is a very important piece of our system. Going back to the overview of the system architecture that we had before, we can now focus on this bottom part, the offline processing part. And it consists of glue jobs that are running Spark and processing data that it outputs to S3. And everything orchestrated by step functions. And as you can see here, we basically have one glue job corresponding to each part of the real-time processing system, right? So for the update state application, we also have a corresponding glue job that does the same transformations, but in batch or in an offline way. And then for the feature calculation, we have a glue job that does the exact same thing as the application does in real time, but also offline instead. So there are two main use cases of our offline processing. The first one being what we call retrospective calculation, and the second one being state backfill. So retrospective calculation is basically applying our feature definition on existing and historical data. So it's all about one question, and that is, what would the feature be at a certain point in time? And then the state backfill is used to repopulate and bootstrap our DynamoDB state table with current state in a cost-efficient manner. So if we start off with the retrospective calculation, it's basically calculating a snapshot of a customer profile at a given point in time, right? So using the old examples, we can say how much is the sum paid amount, or the paid amount feature on customer 1 2 years ago, for example. Or it doesn't need to be a feature that is live. Maybe you're experimenting with feature X on your development branch, and then you can apply that on customer 1 2 years ago as well. So the input to this retrospective calculation consists of a set of customer identifiers in combination with decision times. So what we then do is enrich this data set with all the feature values for that specific customer at that decision time. And this is used to experiment with features, iterate, and used for model training. And then it's also used for analysis purposes as well, such as change impact analysis. If we look at the setup for the retrospective calculation, it looks something like this. So on the left side here, we have our data sources on our Kafka topics, right? At Klarna, we are exporting these to S3 on a continuous basis. So basically that means that we have the full history of all the events that exist on S3. But then if we start off from the dataset requester that is requesting the retrospective dataset, they would create a dataset with customer identifiers and decision time combinations that are interested in. And then we have our update state glue job that would take this input dataset and find all the relevant events for that set of customers. And taking those events and then creating states out of them based on the business logic library that we have defined before. So it's using the same logic that our update state application is using. One thing to consider here is that input dataset also includes a decision time. So basically what we do in the update state glue job is we are also filtering on the decision time itself. So we're only including events before our decision time, right? So we don't want to include things that we don't know of at that point in time. These states are then output into a dataset on S3, and then it's picked up by our feature calculation glue job that applies the feature definitions on top of these states to get all the feature values. And then we have a dataset on S3, and the same dataset requester can access that data and do whatever experimentation they want to do. So if you take a very concrete and simple example, let's say we have this input dataset. So we have 3 customers, although we have 2 decision times on our first customer here, one in 2020 and one in 2023. So first of all, we take this data set and join it with all the events we have, find the relevant events, create state out of them. And then the output of that could look like something like this. And if you note here, the row 1 and row 2 have different states. And that is because state 3 here was created after 2020, but before 2023. So basically for the first decision here in 2020, we didn't know about state 3, right? So therefore we're not including that for row number 1. Then we feed this through our feature definition calculations. And then we get all of our feature values. Here I only listed the example of paid amounts for the customer and decision time, right? So in this first example, we have, or the first row versus second row, we have different amounts, right? Because it's considering different states, right? The first one only 1 and 2, and the second one is considering 1, 2, 3. So the power of this retrospective calculation is that we can apply our new feature definitions on our historical data, which basically means that we don't need to wait and collect data anymore, right? So we can take our new feature experiments, or we can just implement our features and apply them on existing data. So we don't need to, the iteration cycle is way faster. And another important thing is that we can also use it as an internal tool within the team. So for example, if you find a bug that you want to fix, then you make a change to the feature implementation, but then you need to be careful about actually changing that, because that can influence the outcome of your model inference, right? So if you have trained the model on data that includes this bug, if you fix that, then maybe that would decrease the performance of your model. So what we then can do using retrospective calculation is we can make a data set with the implementation without that change, and then we can compare it to a data set with that change, right? And then we can see the differences in feature distributions and how it affects the distribution, and if it will affect the model performance in the end. So the other important use case of our offline processing is our state backfills. So to recap, it's all about repopulating and bootstrapping our state table that we have in our real-time application. And when is this needed? So this is needed when we are changing the updating logic in some kind of way, or if we're changing the data model. So if we're removing or adding fields to our data model, right? And then we don't only want to apply the new incoming events from our real-time data streams with that new definition, but we also want to apply the old past events as well with our new definition that we have in our update state logic. And why we are doing this offline is because it's cheaper to process, more cost efficient to process the full history in batch. So these data sets are usually huge. And also we don't need to consider things as data retention on our Kafka topics. So we don't really have access to the full history on Kafka in our real-time system, right? So the state backfill looks like something like this, the setup. So it's very similar to the retrospective calculation, but even more simpler. So once again, our data sources are exported to S3 with full event history. And then we have our initial glue job that is creating the states. But in this case, we don't need to consider any input data set. We just take the full history of all the events that we have, process the data, and create states for every single order. And we don't need to consider any decision time here as well, right? Because we basically want the current state of all the orders. So we just process all the data we have up until this point. Then we create the states, format them nicely into DynamoDB JSONs so that we can use something called DynamoDB S3 import. And this takes a data set on S3 and creates a new DynamoDB table out of that data set on S3. Then we can start writing to that new table using our real-time state update application. And whenever we're ready, we can switch our feature calculation application to read from that new DynamoDB table as well, right? And that basically means that during this process we have two DynamoDB state tables up and running at the same time to basically ensure that we have zero downtime. Right, so we can summarize all of this by looking back at the list of requirements that we had before and the pain points that we wanted to fix. So first of all, strict contracts between the producers and consumers that we solved by having strictly defined event streams with defined schemas and defined events that basically makes our consumers able to make the right interpretations and assumptions on data. On cost efficiency and scalability, we solved that by now only processing data in real time, so we only really process the changes that is happening to the orders, right? As opposed to the previous setup where we needed to reprocess the full history every single time. And that in combination with our offline processing and our cost-efficient way of state backfilling using DynamoDB S3, we have a more cost-efficient and scalable way that is hopefully scalable for Klarna's growth. And the third part is reducing the differences between batch and real time. This we solved with our business logic libraries, that is separating the business logic from the architecture and the runtime itself. So now when we add features and change features, we only need to do it to our library and it's automatically propagated to whatever it's running on. And the fourth point about experimenting with new features and historical data, that is enabled by our offline processing and our retrospective calculation capabilities. So now we don't need to wait for data to mature, but we can enable. We don't need to wait for data to mature, and we have enabled faster feature engineering iterations. So when implementing this, we came across a lot of hurdles and challenges as well. I'm going to name 3 of them that I think are interesting to discuss. The first of them being the data modeling problem, and that is a problem that is very domain specific and very complex, and it depends on your data that you're processing, the questions you want to answer with your features, as well as your requirements on your systems. So both on data freshness and your latency, right? And it's very important as well because it's kind of the interface of your setup. So whatever you're deciding or defining in your data model, it's going to heavily influence all of your implementations in your business logic and in your applications. And one of these specific challenges is on deciding on the performance on read versus flexibility on read. So the thing I mentioned before in the presentation, and our team basically started off with something that was very flexible because we wanted to experiment with the features and our offering a lot in the beginning. And then we, as our product grew and our stakeholders were requesting more on our services, we needed to like trade off that in order to gain read performance instead. So sacrificing the flexibility we had. The second challenge that we still have is on our offline processing part, and that is that we're running Python UDFs on Spark, and that is not the most efficient thing because it needs to serialize data and you need to communicate that through JVM and the Python interpreter and such things. So if you have a lot of experience with this or good ideas, please come and chat with me afterwards. And the last challenge or the last learning is that the quality of features will only ever be as good as your source data. So no matter how technically perfect your system is or implementation is, you will still have challenges in the content of your data. So what we found out is that most of the issues we have is actually related to the content of the data. So we spent a lot of time trying to understand the data sources we have and understand the corner cases that we have in our data sources And we also learned that it's well worth the investment to invest in data validation tools and data monitoring, as well as tooling to enable the developer to easier debug the corner cases and visualize our data flows from our raw events to our features themselves. All right, congratulations to making it to the end. I hope you have gained some inspiration or some ideas that you can apply on your own systems. And I'll be in the area down here if you have questions or want to chat a bit more. Thank you all for attending this session, and hope you all have a wonderful reInvent week. Thank you.